Hello. This lecture is Module 1 from SWAYAM ARPIT course entitled as Low Energy Integrated Analog to Digital Converters. And the Module 1 is focused on insights into energy consumption in successive approximation register ADC switching. Outline of this lecture is as follows. First, we will see recent examples of application of SOR ADC in system on chip for IoT, Internet of Things applications. Then we will have an overview of capacitive SOR ADC, which is very popular for low energy SOR ADC applications. And finally, introduction to power saving in SOR ADC. Before starting the main content, it's important to know that how useful is this architecture. And therefore, I want to show you two recent examples of published works by industry in this area. The first example is Qualcomm Black Ghost system on chip for IoT. This product is a commercial product, but also it has been published in 2018. And I have written the paper title at the bottom of this slide. So interested audience may refer to that paper. So the block diagram of this SoC is shown in the slide. The first thing you may notice is the availability of 4 different voltage levels, which is very common for energy management in low energy system on chip ICs. So you notice that in addition to battery, we have voltage levels of 1.8 volt, 1.05 volt, and 0.55 volt available. 0.55 volt, which is a low voltage, simply 500 millivolt practically, is used for digital modules which operate in sub-threshold, and therefore it keeps the energy consumption low. We have a power management module which is directly connected to the battery, and this power management part directly works with battery. Therefore, naturally the input voltage to this module is battery voltage. And then we have the analog front end, which includes low noise amplifier and buffer, automatic gain control, and 12-bit SOR ADC, which is the focus topic of this lecture. So this part operates at 1.8 volt because analog and mixed signal modules like ADC show better signal to noise ratio at higher levels of supply and better linearity. And that's why here they are operating at 1.8 volt. Also, some other mixed signal modules like PLL and clock generator units all operate at 1.8 volt. And finally, timer and controller are operating at 1.05 volt and they are always on. So this is a very interesting example of a complete SoC for IoT, and you notice that 12-bit SOR ADC is the choice of architecture for this application. The second example is Intel 14 nanometer low power SoC for IoT. So the previous example was in 28 nanometer and this example is in 14 nanometer. Again here you notice availability of 4 different internal supply voltage which are generated by the power management unit. The same standard 0.55 volt is used for many parts of the digital modules. 0.8 volt specifically is used for a dense embedded SRAM. 1.05 volt, similar to Qualcomm's SoC, is used for the wake-up radio, which also has an SOR ADC, which is a 6-bit SOR ADC, operating at high sampling rate of 4 megasample per second, and 0.8 volt, which is used for dense SRAM, and 1.7 volt, which is used for I/O and gated I/O. So interesting point here is the low supply voltage of 0.55 volt also can be used and is used for other parts of the circuit, which is eventually sensor analog front end. That includes analog sensor interfacing, programmable amplifier, 1 megasample per second 12-bit SAR ADC. So number of bits are similar to Qualcomm's SoC, and finally digital control. So therefore, you can see that SAR ADC is a choice, is one of the choices in recent SoC applications. And you may refer to reference paper published again in 2018 for this SoC, given at the bottom of this slide. So now, let's look at the overview of capacitive SAR ADCs. I don't want really to talk about details of operation because you are familiar already, but I want to show you a different angle of the operation which is not very common in textbooks, and that comes with single supply SAR ADC. So first we will move on to the simple diagram which shows the basic concept of SAR ADC. Here on the left side, you see quantized levels in units of LSP, and on the right side, you see digital output of the ADC. Every SAR ADC has a DAC output because it has a loop in which DAC cycle by cycle, output of the DAC cycle by cycle moves to a quantized levels which is becomes closer and closer to the input level. So therefore, the digital output is actually the input of the DAC, and the quantized analog output is coming from output of the DAC. And because it is cycle by cycle, therefore every conversion cycle is one step towards input voltage. So here input voltage is shown at some arbitrary level between 5 to 6 LSP with dotted blue line, and the DAC output, which tries to reach to the input, is shown by the red color. And as you know, the process starts with the first code, which has MSB 1 and all bits 0. Input is compared with this analog output of or quantized analog equivalent of this code, which is coming at the DAC output. And then if input is more than this quantized level, the next bit becomes 1 without changing the MSB. Therefore, the next code becomes 110. And then because in the next step in this example here, the input is below the quantized level, therefore, the second bit goes to 0 and the third bit becomes 1. Because this simple example talks about 3 bits, so the conversion stops at the end of third cycle. So this is the concept, and I'm sure most of you are familiar with this concept of conversion. So when we use capacitive DAC or charge redistribution DAC, we take advantage of almost close to 0 static power consumption. And that is the reason capacitive-based SAR ADC is very popular for low-energy SAR ADC applications. However, most of the applications today are also single supply. And you see in many textbooks, this point is not well presented. So today I want to show you how you can really consider the single supply system right from the beginning. Of course, because of the supply scaling, most of the ADCs are differential, but for simplicity, I'm using a single-ended configuration. This configuration is easily extended to differential architecture. First of all, when we are dealing with a single supply system, the comparator, which is one of the important parts of this SAR ADC, also is single supply. Therefore, as you notice, it has a supply of VDD and the VSS is 0 level. Since we have a common mode level, therefore we should see how input voltage and reference levels are defined with respect to the common mode level. As far as input is concerned, here you can notice an arbitrary input, which is changing around VCM. In other words, input voltage has an average level of VCM, and then it can change up to VCM plus V full scale by 2 and down to VCM minus V full scale by 2. And the difference between the top and bottom level is V full scale range, which is shown here. So therefore, V full scale of ADC can be defined around VCM. So we go with this definition, and therefore we will have the switching circuit shown in the left side. The module which is shown in the orange color block is actually capacitive DAC. And the switching arrangement is a little different from what you have seen in most of the textbooks. The reason is because here we have a common mode level, and the reference levels are defined with respect to common mode level. Therefore, we have two reference levels here. One is the minimum value of the reference level, which is VCM minus V full scale by 2, and one is the maximum level, which is VCM plus V full scale by 2. We have the common mode level, which is actually 0 if we would have had dual supply, and we have also common mode level used for initializing the capacitors. Similarly, comparator also will have common mode as the reference input, not ground as a reference input. So, steps are similar to dual supply with a slight difference in the actual results. So, we will see how it is happening. First, always we have sampling of the input at bottom plate of capacitive DAC, which is happening by keeping the switches in the position shown in the figure. All of them are connecting input voltage to the bottom plate. So, this is an example of 3-bit ADC for simplicity of the operation. And the top plate is initialized at common mode level by closing switch SS1. So, this is the first step of the initialization. We move to the second step. So, in the second step, eventually the bottom plate is connected to the common mode level, and therefore, the voltage on top of the capacitors, which is achieved after opening the switch SS1, will become 2 VCM minus Vin. So, you may be surprised, what's the use of 2 VCM minus Vin? To understand, assume a better way of writing this voltage. You write it this way, VCM plus VCM minus Vin. So, first VCM is the common mode level. Therefore, when it enters the input Vx, enters into the comparator, when comparator has to decide, compares VCM plus VCM minus Vin with VCM. Now, if you remove VCM from both positive and negative terminals or deduct it, it is equivalent by saying that we are comparing VCM minus Vin with 0. And because Vin itself has an average value of VCM, so therefore it is equivalent by saying that we are comparing incremental values of Vin with respect to VCM and 0, which is exactly same as what we achieve when we are using a dual supply. So, operation is exactly same as before, but voltage levels are controlled this way, so that the single supply operation is possible. So, now the similar example that we had before, but with a different value and single supply switching is shown in this slide and covering all cycles. So, on the left side, now you see the common mode levels that I have put for you are not just simply negative to positive, but actually the common mode level is also included. So, therefore, the minimum quantized level is VCM minus V full scale by 2, and the maximum common mode level is VCM plus 3V full scale by 8. So the arbitrary input, which is slightly below VCM, is shown by blue color, and the operation over 3 cycles for generating the corresponding code is shown by the red color. On the right side, you see the corresponding switching. So first, we have the initialization. So this is the same initialization step where we connect the top plate of capacitors to VCM and bottom plate to Vin. Eventually, we are charging the all capacitors to VCM minus Vin. So these capacitors are binary weighted, and we have one capacitor with value of C, which is the unit capacitor available, in addition to LSB capacitor. So in the next step, we are initializing Vx, which was shown in the previous slide, which is the top plate value, to 2 VCM minus V. So this is summary of the switchings which happened in the previous slides. Now we want to move to the first bit. So now if we consider the first bit, so we need to see that what will happen, whether this first bit will tell us it is the reference should be with respect to VCM minus V full scale by 2 or VCM plus V full scale by 2. So here is where we are talking about the sign of input voltage with respect to VCM, whether input is above VCM or input is below VCM. So this decision is made right from the beginning, because at the input eventually we are comparing VCM minus Vin with VCM. Therefore, the output of the comparator will tell us about the sign of input with respect to VCM. So in this case, VCM is above input. That means VCM minus Vin is positive, or Vin minus VCM is negative. Because Vin minus VCM is negative, therefore we start from VCM minus V full scale by 2, which is shown over here, to generate the next supply, the next reference level. And this reference level eventually is the original value minus V full scale by 4. Therefore, Vx changes to 2 VCM minus Vin minus V full scale by 4. So this is the value of Vx, and effectively equivalent reference which is produced is VCM minus V full scale by 4, which is shown in the left diagram. And then because input voltage is above that, therefore in the next step, the VCM minus V full scale by 2 point will be returned back to VCM, and the next reference level will be set at VCM minus V full scale by 2, and the effective Vx will be 2 VCM minus Vin minus V full scale by 8. So this level, which eventually corresponds to the reference level of VCM minus V full scale by 8, is shown on the left, and therefore the code corresponding to the input, which is 0, 1, 1, will be generated by ADC. So now we know about the examples of a single supply switching scheme. Now, how this switching power or switching consumed energy contributes to the total energy consumption of a SAR ADC over the entire set of cycles of conversion when all bits finally are generated at the output. So to get some idea, one of the published works related to this matter is referred here from D. Zhang, which is published in IEEE Journal of Solid State Circuit in 2012. It's about implementation of a 9-bit, around 9-bit, low energy SAR ADC with sampling rate of 1 kilosample per second in 130 nanometer CMOS technology. So it's good to look at this pie chart and get some idea of the practical contributions. In this application, analog and digital supply both are 1 volt. Total power consumption for the one complete round of conversion is 72 nanowatt at sampling frequency of 1 kilosample per second. Now it's very interesting to look at the contributions. First of all, if you look, comparator power dissipation is only 3% of the total power dissipation, which is very low. Therefore, it's not a bottleneck of energy consumption. The next contributor comes from the dynamic power in the digital modules, digital parts of the system, which includes also the control logic. So that contributes 20%. The next contributor is the leakage of the system, because the digital system will contribute if the energy levels are low when it is in a static mode. And interestingly, here it contributes 31%, which is a significant value. But main contributor is actually DAC. Therefore, DAC switching is a very important point to be considered for energy reduction in SAR ADC. So, since now we know that DAC contributes to the energy consumption significantly, so let's have an introduction to see how we can save power in SAR ADC. And for that, let's have a look at how energy is consumed in the charge redistribution DAC, which is happening due to the switching of the capacitors. So here is an example when one of the capacitors is switching. So let's assume in this case we are in the time capital T, and the configuration of the SAR ADC is shown here. For simplicity, here I am showing only V full scale and 0, because here the main motivation is about switching, and then show how this switching changes the energy dissipation. So here capacitors are same as before, binary weighted. So we have capacitor C0, C1 which is same as C0, and C2 which is 2C0. So the initial condition has been in such a way that C2 is connected to V full scale and C0 and C1 are grounded. And Vx is the same Vx which was shown in the previous slides. It's eventually connected to the negative terminal of the comparator. So when we have a transition from one reference level to the next reference level for the next conversion cycle, which is called time 2t, we have energy consumption. So what is this energy consumption coming from? It's drawn from V full scale. So therefore, we are concerned about the energy which is drawn from V full scale. So here C1 is switched to V full scale, and therefore it's a single capacitor switching. So what will happen? DAC output at the beginning was minus V in plus V full scale by 2, because C2 has been connected to V full scale. Now by connecting C1 to V full scale also, so the reference level changes to 3 by 4 V full scale. So this is the way operation is going on. So we want to see how much is the energy consumption. To calculate the energy consumption, we should focus on V full scale. Two capacitors are connected to V full scale. And interesting point here is, when capacitor C1 is connected to ground, bottom plate of C1 is 0. When C1 is connected to V full scale, the same plate is connected to V full scale. That means polarity of the voltage across C1 has to change. And because of that, it will draw energy from V full scale. Capacitor C2 also will have change in the voltage because Vx will change. Therefore, we will calculate variation of the voltage across the two capacitors from time t to time 2t by just considering the voltage difference across two capacitors, multiply by value of the capacitor, which will give us effectively the amount of charge which is drawn from V full scale, multiply by V full scale, and that will give us the variation of energy. Because here we are looking at Vx minus V full scale, therefore minus V full scale is written instead of plus V full scale. So this energy is calculated at 1/4 C0 V full scale square. So this is a simple example of how to calculate energy consumption for single capacitor switching. So you may be curious to know how much is the actual value, typical value of this value, 1/4 C0 V full scale by 2. So here we provide a numerical example. Let's assume V full scale is 1 volt, which is a typical number. Unit capacitor is 5 femtofarad, which is a typical number towards low side, but let's assume values are small. And input voltage, which is 0.3 volt, which is a typical number. So now if we have same example we had before with these values and calculate the change in the voltage values and therefore effective charge which is drawn, so we will see the value will be 1.25 femtojoule. Therefore, this single supply switching moving from Vref by 4 to 3 Vref by 4 reference results in 1.25 femtojoule power dissipation. Notice this power dissipation is proportional to C0. So therefore, if suppose I increase C0 to say 20 femtofarad to have larger capacitor to improve the mismatch issues, to improve the behavior of the DAC with respect to mismatch issues, correspondingly, I will increase the power energy consumption by a factor 4. So now what will happen if we have 2 capacitor switching? 2 capacitor switching also is happening in some cases. These cases is when we are moving from a higher reference, for example, to a lower reference. Here example is when we are moving from V full scale by 2 to V full scale by 4. So in this case, C2 is same as previous example connected to V full scale and C1 is connected to ground. Now C1 will be connected to V full scale and C2 to ground. And because polarity of both C1 and C2 is changing in opposite direction, energy consumption we expect to be more even, which is true, it will be even more. In fact, if you write the expression the same way we have written here, you will see it will become 5/4 C0 V full scale square, more than even C0 V full scale square. So therefore, we have energy consumption because of this switching of 2 capacitors and they are changing their charge in opposite polarity. So now we have learned about some basic ideas around how to calculate energy and what points to consider with respect to energy reduction. Means we have in mind that because energy consumption comes because of change in the polarity of the charge across capacitors and that is drawn from supply. So if we can somehow relax this phenomenon, we would be able to reduce the energy. So we will keep as a learning point and we will move on to the next point, which is very common and I have explained it even at the beginning to show you how in system-on-chip applications for IoT, different supply levels are used to minimize the energy consumption. Energy saving can be performed by operating different blocks of the circuit at different voltage levels. For example, here the logic level is less than the voltage level which is used for the DAC. Here the supply level is 1 volt for the DAC and 0.4 volt for the SAR logic. And one level shifter is used to convert the output of the SAR logic from low voltage to high voltage, which is 400 millivolt to 1 volt, which is used for switching the switches. Therefore, comparator also will be able to work at reasonable voltage, which is 1 volt here, without being affected by the limitation of the voltage on the SAR logic. And in this way, energy will be saved. Also, one of the common techniques for level shifting in digital modules is shown in this figure. So eventually you have a cross-coupled circuit, and then you have a low voltage part, which is shown by VDDL, inverters with VDDL, and the high voltage part, which is shown by VDDH on the upper side. So now by taking the outputs from the outputs of the transistors en masse, which are shown here, you would be able to eventually limit the voltage to the voltage controlled by the input inverters. So now if we go with this scheme, how power energy consumption will change. So we go back to the same example. Left side is the example that we had before, and on the right side we have the same circuit by just changing the digital supply from 1 volt to 400 millivolt. Now initial power consumption, which is 72 nanowatt at 1 kilosample per second, changes to 53 nanowatt, which is the value reported in the paper, same paper from Zhang. And here you see the contributions now. Now very clearly you see contribution of the dynamic logic, which is shown by digital dynamic power, is reduced from 20% to 9%. It's very interesting. And contribution of now SAR ADC, the DAC part of SAR ADC has increased to 62%. So therefore now we can see the focus area should be, after multi-supply solution, should be reduction in the energy of the DAC. And this will be achieved by designing proper switching schemes for charge redistribution DAC or capacitive DAC. So conclusions of this module are as follows. SAR ADC is widely used for low power applications, in recent SOCs for IoT applications, as we see even by commercial reports. The capacitive DAC in SAR ADC consumes significant power, and therefore it's a matter of concern for energy reduction. DAC size and also energy consumed in DAC switching approximately doubles as we increase the DAC resolution and naturally ADC resolution. This is because value of capacitors increase, and therefore we will have more number of capacitors and more number of switchings. Therefore we expect to have more energy consumption for every watt which is generated. For low sampling frequencies, even leakage in the static power of the digital circuits contributes to the power dissipation. And finally, to reduce the dynamic power, we can operate digital circuits at low supply voltage, which is the common trend in recent reported system on chips for IoT applications. We reach to the end of this lecture. Wish you all the best.